Hello everyone. So today our group will be presenting on the rocket engine converging diverging de Laval nozzle system for fluid mechanics 2. So our team consists of 6 members, which is Nurul Wajihah, Muhammad Akif, Muhammad Shafiq, Muhammad Hafizul, me myself, Muhammad Ghifakul, and Nurin Batrisha. So to kick off the introduction, let's look at the background of rocket engine nozzle system. So for rocket propulsion system, fundamentally work by converting the chemical energy stored in propellants into high velocity kinetic energy, which will generate the thrust. So inside the combustion chamber, there is high pressure and high temperature gases exist at near stagnation condition. It represented by PO, P naught or T naught. So to accelerate this gas, a converging dart first increase the subsonic flow where Mach number is less than 1. So up to sonic flow where Mach number equals 1. However, to achieve supersonic flow where Mach is greater than 1, a converging diverging or de Laval nozzle is required. So as gas pass through the narrow choke throat and enters the expanding cross-sectional area of the diverging section, the static pressure and the temperature continuously decrease while the gas velocity is increased. So it will drive the high speed of the exhaust.
Nuri, and I'll be presenting the relevant to fluid mechanics too. So, the converging diverging nozzle is a practical application of fluid mechanics too. As gas density changes due to pressure and velocity variation, the fluid is analyzed using compressible fluid dynamics, and the key fluid mechanics concept directly applied in this report. So, there are six key fluid mechanics concepts. So the first one is stagnation and static properties, which is relating reservoir conditions to local state variables along the nozzle flow path. The second one is choke flow and critical pressure ratio, identifying the physical limit where fluid velocity reaches sonic peak, fixing maximum mass flow rate. And the third one is speed of sound and Mach number, classifying flow regimes using local sound speeds. The fourth one is area Mach number relationship, analyzing how geometric expansion ratio dictates local flow velocities. The fifth one is isentropic flow relations, governing property changes across changing depth cross sections, assuming reversible adiabatic processes. The last one is shock wave behavior, understanding normal and oblique shock wave dynamic caused by back pressure mismatches at the nozzle axis. That is the objective. So the first one is explain nozzle geometry and working principles. The second one is describe compressible flow behavior, explain choke flow. The fourth one is discuss important compressible flow equations. And the next, explain effect of varying ambient pressure on nozzle condition. The last one is discuss engineering applications. Okay, next, nozzle geometry and working principles. So we have five main parts, which is combustion chamber, condensation, fluid diverging section, and nozzle exit. And the working principles are gas starts at high pressure and temperature. The second one is condensation accelerates subsonic flow. The third one is flow reaches Mach 1 at the third. The last one is diverging section accelerates gas to supersonic speed.
Okay, for next, let's look at how convergent and divergent nozzle works using compressible flow mechanics. So as hot gas travels from the combustion chamber towards the exit, a fascinating trade-off happens. Its velocity shoots up, while pressure, temperature, and density also drop. So focusing specifically on the converging section, which is the physical space, gets narrower. This narrowing acts like an accelerator for subsonic flow. So pushing the gas faster as it approaches the nozzle tightest point, known as the throat. So where the Mach number is still less than 1. So that is all about what is it in this slide about compressible flow behavior. Other than that, let's talk about choke flow. So right at the throat, the narrowest part of the nozzle, the gas reaches a critical speed where its velocity exactly equals the local speed of sound, meaning the Mach number is equals to 1. So when this happens, the nozzle enters a state known as choke flow. Once the flow is choked, two very important things occur is the first one is the maximum mass flow rate and the second one is flow limitation. So the throat effectively acts as a bottleneck, capping the maximum amount of gas that can physically pass through under those operating conditions. And for the second one is no matter how much further you lower the downstream ambient pressure, the gas simplify cannot flow any faster through the nozzle. So in short, choke flow is the maximum flow rate and serve as our ultimate gateway to achieving supersonic speeds downstream. So that's all for about choke flow, and we will proceed to the next topic.
Next, I will explain the supersonic flow in divergence section. After the gas reach Mach number equal to 1 at the throat, which is called choked flow, it enters the divergence section of the nozzle. In this section, the nozzle becomes wider. Unlike subsonic flow, this larger area allows the gas to expand and accelerate to supersonic speed, which means the Mach number becomes greater than 1. During this process, the gas converts thermal energy into kinetic energy. This means the heat energy is changed into the energy of motion, so the gas moves much faster. As the gas moves toward the nozzle exit, its velocity and Mach number increase while its pressure, temperature and density decrease. The equation shown here tells us that the total energy remains constant. As the gas expands, some of its thermal energy is converted into kinetic energy, which increases the flow velocity. This high-speed exhaust gas produces a greater thrust, allowing the rocket to move forward efficiently. Now, I will briefly explain one of the important equations used in the convergent divergent nozzle. This equation helps engineers understand how the gas flows through the nozzle and predict how much thrust the rocket can produce. The first equation is the continuity equation, which is based on the conservation of mass. It states that the mass flow rate remains constant throughout the nozzle. In simple words, the amount of gas enter the nozzle is the same as the amount of gas leaving it. The equation is mass flow rate equals to density times area times velocity. And next, I will pass to Hafizul. He will be explaining the remaining important equation.
These are the equations that used to analyze compressible flow inside a converging diverging nozzle. So the first one is the Mach number equation, which is the ratio between flow velocity and the local speed of sound. It allows us to determine whether the flow is subsonic, supersonic in a rocket nozzle. So the flow reached Mach 1 at the throat before becoming supersonic in the diverging section. So the second equation is the speed of sound equation. It shows that the speed of sound depends on the gas temperature. As the gas expands and cools inside the nozzle, the speed of sound decreases, which also affects the Mach number. Next is the temperature ratio equation. It explains that as the Mach number increases, the static temperature decreases because thermal energy is converted into kinetic energy. Finally, the pressure ratio equation shows that the static pressure also decreases as the gas accelerates through nozzle. Together, this equation describe how pressure and thermal energy are converted into the high-speed exhaust needed to produce rocket thrust. Okay, so next is the area Mach number relationship between the nozzle geometry and the flow velocity. The area Mach number equation relates the nozzle cross-sectional area to the Mach number of the flowing gas. One important point is that there are two possible flow, which is subsonic and the other one is supersonic. As shown by the graph, when the area ratio equals to 1, the flow reach Mach 1 at the throat. So this area we call it critical area. So before the throat, the converging section accelerates subsonic flow. After the throat, the diverging section accelerates the gas further into the supersonic region. This explains why a converging diverging nozzle is required to achieve supersonic exhaust velocity and maximize rocket performance. Okay, this explains the three possible nozzle exit conditions. The first condition is under expanded flow, where the exit pressure is greater than the ambient pressure. In this case, the exhaust gases continue expanding outside the nozzle, meaning not all the pressure energy has been converted into kinetic energy. The second condition is perfectly expanded flow, where the exit pressure equals the ambient pressure. This is the ideal operating condition because the exhaust leaves the nozzle at maximum efficiency and produces the highest thrust. The final condition is over-expanded flow, where the exit pressure is lower than the ambient pressure. The higher outside pressure forces the exhaust inward, creating shock waves and sometimes flow separation inside the nozzle. These effects reduce the overall thrust and nozzle efficiency. Therefore, a rocket nozzle should ideally operate under perfectly expanded condition to achieve the best propulsion performance.
Furthermore, the level nozzle is widely used in many aerospace systems because it helps produce high-speed exhaust gases and strong thrust. Common engineering applications include launch vehicle and liquid rocket engines that used to generate enough thrust to lift rockets into space and overcome Earth gravity. Next is solid rocket motors. It is commonly used as booster rockets to provide extra thrust during launch. Then spacecraft propulsion and satellite thrusters. It is used to move spacecraft, change their orbit, and control their direction in space. And lastly, experimental rocket propulsion system. It is used by researchers to test new fuels, engine designs, and materials under high-speed gas flow conditions. Last but not least, conclusion and summary. At first, converging diverging nozzle accelerates gas to supersonic speed, which then choke flow occurs at the throat, which makes the Mach number equal to 1. And then the thermal energy is converted into kinetic energy, where the thrust is produced. As the gas moves toward the exit, the pressure and temperature decrease, while the gas velocity is increases. And lastly, ambient pressure affects the nozzle performance. With that being said, that's the end of our presentation from Group E about rocket engine converging diverging the level nozzle system. Thank you.